So we're just implementing this model. And all I did was copy and paste the calc posterior from above. And so all we need now is, instead of gammas, we need binomials, because our likelihood is binomial. This is a deterministic transformation here. And so I need this I need actually the inverse logit, which is this. And so priors on the slope and intercept are there. Calculate p from a plus b times x, where x is the log dose. And then the data likelihood is just summing over all of the observations. So the log PMF of the binomial for every observation. And every observation has its own p, because p is a function of dose. But n does not change. There's always 5 rats in every cohort. For some reason, I've diverged here. So in the interest of time, I'm not going to debug my own crappy code. Anybody have a question about that? I've just made a silly mistake somewhere, I'm sure. But you'll never have to do this, because I'm going to show you how to use PyMC. It's another reason I'm not going to bother debugging this code. Okay. So, so that's kind of an illustration why we want PyMC, right? We don't want to write a new MCMC algorithm. Actually, even there, I didn't rewrite it, right? All I did was rewrite calc posterior, but even then, it's a little fiddly, right? We don't want to re-implement for every model, and that's, you know, what you would have had to have done before some of the current software had been made available. Okay, so you ask somebody for their model, they send you, you know, 10,000 lines of Fortran code that's tied to a particular model that person is solving. So you don't want to write a new, just like you don't want to be a frequentist and come up with estimators for everything. You don't want to write an MCMC implementation every time you do a problem. And so that was one of the big limitations until sort of the early 90s, when the WinBugs project came about. You really had to code it by hand, which really limited the number of people that could use MCMC. And now there's more packages, right? There's OpenBugs and Bugs and JAGs, which are, they're kind of evolutionary dead ends. I can talk to you about that later if you want to, but they, by the developers' own words, they're kind of evolutionary dead ends. There's 0.3 developers working on OpenBugs. Okay? OpenBugs is written in component Pascal, so feel free to contribute if you want to. So one of the reasons for doing things in Python was that I didn't want to write my Bayesian models in bugs. I didn't want to write an R over here and then have to write my model in bugs over there. I want to write Bayesian models in Python. Right? I don't want to switch around as much. And so the idea is, we implement MCMC in a general way in Python, because usually the base stuff is just a component of your larger analysis. Right? I get to use pandas and stuff like that when I do my data analysis. That's great, and that's because it's written in Python. And so, so what PyMC does is it gives you a lot of the important MCMC sampling algorithms, along with a whole bunch of other functionality. It's got all of the distributions you'll ever need that are coded in Fortran. So one of the downsides is installing PyMC can be a little tricky, because you have to compile Fortran extensions, which can be problematic for some people. But that makes them very fast. One of the things that slows down Metropolis Hastings is that you have to evaluate likelihoods at every iteration. And that gets expensive. And so they're written in Fortran so they can be as fast as they possibly can. You can customize your sampling. You can make it interactive if you want to. There's a lot of really nice plotting functionality, summary of posteriors. You can save your traces to a variety of backends, including SQLite, Pickles, HDF5 if you want, convergence diagnostics, which we'll talk about, and it's very easily extensible. You can, if you want to implement a newer MCMC algorithm that's not in PyMC, you can do it relatively easily. If you want to implement a different probability distribution that we don't add to it, that we don't have, it's easy to do that. So I just want to give you kind of an overview of looking at just a simple model in PyMC, and I'm going to give you the model we just worked on, which is this regression model. So it's the housing prices model. And so this is what PyMC looks like. Oh, no thank you, Droppler. I specify priors using statements that specify the particular distribution that I'm using. Similarly for the tau, so this was the precision of the normal. It's gamma distributed. I don't have to dig around for SciPy functions. I create a PyMC object that's a gamma distribution, and I declare that with its particular values. I calculate a linear function of the housing price, decorate it with a thing called deterministic. We'll get into what that is. Makes it a deterministic node. And then here's a sampling distribution for the prices. That implements that model. Okay. So it's pretty concise. This is what you would sort of write if you were writing it on a whiteboard, and that was kind of the goal. Okay. There's nothing in here except what involves your particular problem. You don't have to know anything about MCMC necessarily. You just have to be able to write down your probability model, and then you let PyMC do it. So how do we do that? Well, we have to pass all of these PyMC objects into an MCMC sampler. So right now I'm just going to call locals, which gives me all of the local variables, and PyMC sifts through and finds its own objects. It can get a little bit dangerous. Oh, what's it doing? Installing extensions behind my back. I'm giving it a pickle backend, so I'm going to save this to a pickle. Oh, I guess I should, here, let me clear all this stuff. I don't want to, there we go. Okay. Oh, what happened? What's happened is that there was already a pickle there that I'm going to delete. Thought there was. No? Okay. There we go. All right. And so it samples 20,000 iterations in the blink of an eye. So it's pretty good. And then there is a lot of, as I said, summary functionality. So here it's showing the posterior distribution of the slope, the trace, just like we saw before. It also does an autocorrelation function, which doesn't look great for this one right now, but that's fine. Okay. So that's the idea. So what we're going to do now is dig in to what each, this is going to be sort of a guided tour through PyMC, which will be fun. I don't usually get to do this. So let's start with that coal mining disasters problem, right? So we've seen this time series before. So we're going to implement this model in PyMC, and we've already seen it, right? Nothing here should be surprising to you. And what I'm going to do with this is to motivate an examination of all of the PyMC objects that get created along the way. So I'm going to dig into what's going on under the hood a little bit here. There are a number of different PyMC objects that represent the various components of a Bayesian model. And so in particular here, tau and the lambdas are these sort of epistemic probability distributions, right? They describe their priors. They describe what an unknown quantity and how much we know about it. And what PyMC does is it wraps a stochastic object around that. And that stochastic represents a value whose, or an object whose value is not known. A deterministic node in this model would be the rates, so a vector of rates. So you need a rate for every year, but there's only two rates, right? There's the two lambdas. And And they're deterministic given the values of tau, lambda 1, and lambda 2. Okay? So it's a little bit confusing in that, well, tau and lambda 1 and lambda 2 are unknown, and so this is kind of unknown in stochastic, but it's completely determined given the values of those parameters at any given time. There's nothing inherently unknown about those rates given the arguments that you pass to it. On the other hand, even if you know the parameters for the lambdas that account for the rates, there's still uncertainty involved, even if you know what those hyperparameters are. So in this case, what we're going to do is we're going to pull out the variables or the stochastic types that we need for this particular model, so discrete uniform, exponential, Poisson, and this deterministic function, which I'll show you later. So when I declare my switch point to be discrete uniform with range 0 and 110, this represents the difference between, what was it, 1964 and 1851 or something like that, 111 years. And I look at switch point, I get this. So this is a discrete uniform object from PyMC. And it represents uniformly distributed discrete variables, okay? Equally likely. Similarly, I give early mean and late mean exponential variables, priors. And then here is this deterministic node, and this determines the rate for every year. So all I do is I write a normal Python function that returns a vector of rates. So I create an empty vector, an empty array, excuse me, and everything before the switch point I populate with the early mean, and everything after the switch point I populate with the late mean, and I return it. And the only difference is here is I use this decorator. Okay? For those of you not familiar with decorators, they're just functions that can be used to wrap other functions to add functionality to them. They decorate that function. In this case, it does all of the goodness of, endowing it with PyMC object properties, okay, methods, and so on, so that PyMC knows what to do with it. All you've got to give it as a user is a function that returns the value given the arguments. Okay. So that's that. And then our likelihood is a Poisson distribution. We're modeling the counts. It's our sampling distribution for the data, right? Looks very, very similar to the declarations for our stochastics, our unknowns. The only difference in here, we look down, we give it a name, we give it it's one parameter, we give it values. The value is different here. I didn't declare values up there. Notice that. Could have, but I didn't. But not only do I give it a value, which is the data, I also set this flag, observed equals true. And this sets it as a data stochastic. Okay, these are your sampling distribution is a stochastic variable. You just happen to have observed it. So you're fixing it. So what's going to happen when you run the MCMC algorithm, the values of the non-observed stochastics are going to change at every iteration. But when it hits these guys, it'll say, oh, it's observed. I can't touch it. And so it'll be fixed. You can still calculate its log probability, but you can't change its value. And it's a little tricky because in Bayes, if you write down the notation for one of these models, where is it? Right here. There's nothing really that distinguishes that as being a data sampling distribution and those as being unknown. It just isn't the notation for it. Similarly, in PyMC, they essentially use the same objects. It's just they're modified a little bit. So what PyMC is essentially doing under the hood is it's building a graph. It's building a graph that relates each of the PyMC objects in the model to one another. And the way that it does that is it identifies, what it's trying to build is a DAG, a directed acyclic graph. Okay? It's a graph where there are no loops. And so every node in that graph either has parents or children or sometimes both. So, and the way that those are determined are via the arguments that you pass when you specify each object. So in this case, in rate, the parents of rate are going to be the switch point, the early mean, and the late mean. Early mean and late mean, the parents are just constants. They're hyperparameters that I chose. And so you can actually query each of these. So the parents will be a dictionary that show the parameters of that, in this case, discrete uniform distribution. Oops, keep forgetting to click through on this stuff. There. Disasters, two parents, mu and rate. The children of rate are disasters. If one's a parent of another, then they has to be, then if A is a parent of B, then B has to be the child of A. The children are specified as a set rather than a dictionary because you don't actually need the labels to calculate the log probability. And actually, you can, if you have PyDot and GraphViz installed on your machine, you can actually generate the DAG for your model before you run it. So here I've instantiated an MCMC object, and I've called graph.dag, and then I run a dot on it from the command line through GraphViz, and that's my model. And I always like to do this because, on a more complicated model, I'll find some unattached node floating out in the corner, and it's an easy way of debugging your model before you, lose your mind. And so it just draws these hierarchical relationships. Okay. Let's see here. So the other, aside from children and parents, the other attribute of note here, two other important attributes. One is the value. So every node will have, every stochastic node will have a value associated with it. So for disasters, we've fixed it to be the data. For switch point, 108, 3.3, 0.85. So if you don't specify an initial value, PyMC will draw one for you from that exponential distribution and from that discrete uniform. I could have up here specified an initial value. Okay. Now I go back down here, and its value will be 1 if I want to. Those values will change. Every time that we update it, it's going to change. Okay. Okay. So it needs to be higher. Okay. The rate, it's going to be, I had them set to be the same value here. It'll be easier if I, so the rate, remember, is deterministic, right? It's just setting the values of the rate conditional on early, late, and the switch point. That switch point was at 108 out of 110, so it's specifying the late here. So this is obviously a very bad starting point, but we don't care. Along with the value, for its particular value, it also has an attribute that is the log probability. Okay? And I can, every time I set the switch point to be a different value, 50, the log probability should change. Yeah, it's uniform, that's right. Thank you. Yeah, so it's uniform variable, so it's going to have the same log probability. Whereas the late mean, it's just down here. Every time I change it, it's going to have a different value. So every time that every time it changes value, it gets a new log probability, which allows it to be evaluated in the context of the joint posterior. One thing that you might have noticed is that I was able to pass a PyMC object in each of these cases, and I used this PyMC object switch point to index as an index to an array, which seems a little strange. And what's really going on here is it's some magic from this deterministic wrapper. What it's doing is it's taking each of the arguments passed to that deterministic and pulling its value out, and so that it's using its value rather than the object itself. So it's just a little bit of magic underneath. All right. The next step is passing it to the MCMC algorithm. So we're just passing, so the model is actually implemented. It's one of the examples. So you can pull, the best way to work with PyMC is to specify your model in a file. And then when you import that file, you can pass it directly to an MCMC, and it'll find an MCMC object, and it'll find all of the objects. Or what you can do, what I like to do in IPython notebooks is I write a function, and the function just returns its locals or its vars, and it'll pass all of those PyMC objects back, rather than having to build a little array that contains all of your individual variables. Okay? And then sampling, which is done this way. And there is an interactive sampler that doesn't work very well in the notebook, but if you're running on the console, if you call iSample instead of sample, it actually allows you to stop, pause, and query while the algorithm is running. You can see what acceptance rates are doing while it's running, but it doesn't work very well in the notebook, as you might expect, because it's hard to interact with a running process in one of these cells. Once you instantiate a model, what it will do is create backends for each of the nodes in the model and populate those with the sample. And by default, it creates traces in memory. So if you're doing several million iterations, it's probably good to switch that. And so every model and every stochastic or deterministic within that model will have its own trace attribute. And you can get that at them a couple of different ways. One is to use the trace attribute of the model itself and pass the name of the covariate or of the stochastic that you want. And so I'm taking the last 1,000 values here of the switch point. Alternatively, you can access the early mean directly and get its trace that way. And so you can, do whatever you want with these traces. You can generate a histogram of them or use the built-in plotting mechanisms. Yeah, see what happened here? Boom, jumped up and it found where it needed to be. So convergence can happen quite fast in some models. In which case you want to cut these out. So there's another argument that you can pass to. No, I did it here. So I passed 10,000 iterations, and I said burn equals 1,000. What that is it specifies a burn-in interval, and what it'll do is it won't save the trace during that interval. So it's throwing away the first 1,000. Looks like I should have thrown away a few more, right? We don't want to be using that for inference. You can thin things as well, but it turns out you really don't have to thin, so I never recommend it. If your autocorrelation is really bad, sometimes thinning helps, but it usually means there's a larger problem with your model.
How would you know if the autocorrelation is bad?
What it does is it reduces your effective sample size. So if it's highly autocorrelated, so if things are very uncorrelated, so if this autocorrelation function drops quite steeply, it's becoming very close to sampling independently. When it looks like that, it just means that you're not getting as much bang for your buck from your sample. So you might sample.
What's actually being correlated there, the trace?
Yeah, it's every individual value. This is showing the lag, the correlation between values. flags of 1, 2, 3, 20. How we call it, referring to one of but it's not. I don't worry about it too much. I just sample more. It's usually cheaper just to sample more. Not cheaper, but easier. This is doing the tuning for us. Yes.
Does the burn-in parameter affect the length of the
So I have it set by default to tune throughout, which actually has been. You can show that it doesn't matter very much. The tuning will settle down on its own, even if you don't shut it off, and so it's not usually a problem. There is another slightly different adaptive Metropolis algorithm that's implemented too that's really good for highly correlated parameters. And what it does is it actually uses the trace as a vector of parameters as a multivariate normal proposal, and it adjusts the covariance structure of that multivariate normal depending on the trace. And that's a relatively recent algorithm, and it works really well for highly correlated variables. Another output I really like is the summary plot. So this generates what we call a little forest plot. So puts the posterior median in the middle, interquartile range is the fat part of the line, and then the 95% posterior interval is the thin part. And it's really nice if you have 100 parameters. It's really a nice way to look at your model as a whole, as opposed to having individual plots like this. Really good for publications and stuff. Alternatively, you can do a non-graphical summary. Well, this is still sort of graphical, but it's just ASCII. Identifies the important posterior samples. This is the 95% highest posterior density interval. It doesn't just lop 2.5% off of each side. That's what these do down here. It actually calculates the shortest 95% interval. There's an infinite number of 95% intervals, right? This is the shortest one, which is what you want. If you just want you can just get a dictionary of the posterior statistics by doing stats as well, if you want to use them somewhere else. One of the nice things that you can do really easily in Bayesian analysis with MCMC is deal with missing data. And missing data is one of these real-world things that you don't get taught a lot about when you take an intro stats course, and what we do about it. One way of dealing with observations with missing values is to drop those observations, right? Which has consequences. You're sort of you're sort of assuming that they're missing completely at random, as we say, and if that's not the case, it can cause some bias. But you're also throwing information away. So here's just a fake data set. This is like a wildlife survey, aerial survey kind of data set where you have an observer that's wandering around and counting, animals or plants or something. And let's say for some reason the thermometer wasn't working and they couldn't record temperature at that site. Well, if we throw away this whole row, that piece of information is missing and we'll never get it back. But there's information here about who was there and what site they were at. You don't necessarily want to throw away, if you've got a row in your database and your database has 100 columns of information, you're throwing it away because one of those is missing. It's not very efficient. But remember, as Bayesians, everything that's unknown is treated the same way. And so missing data is no exception. We treat missing data essentially as an unknown parameter. It's just something we don't know. We just insert it into the model. And in particular, with missing data, we're able to sample from what's called the posterior predictive distribution. Posterior predictive distribution is this expression right here. F of theta given y is our posterior. Y tilde is a missing value. You can think of a missing value as something that you missed in your current data set. You can also think of it as future data or data that you just didn't bother to go out and collect. So here's our posterior of theta given y. Now we want to know, we want to be able to see what, given what we know, what is that missing, what's the value of that missing data point? And then we just have to integrate over theta, right? Integrate over what we don't know. Looks like another scary integration that we have no idea what to deal with, but as it turns out, you actually get this for free. It's one extra line of code in PyMC to sample from the posterior predictive distribution. Because remember, we get all these marginals of our unknowns as outputs. And so all we have to do is create a node for our missing data, and we can run with it. So I just artificially went into the disasters data set and deleted a couple of points. So I substituted values, integer values with nones. You can put whatever you want there, -999s or what have you. Better execute these. So what PyMC does, what we've done is we've made use of the NumPy masked array. And so what we're going to do is create a masked array of our data where the value equals, wherever the value equals none, it knows that it's a masked variable. So we can see here that they've identified those. And so PyMC, when you pass that masked array rather than the original data array to the likelihood, to that observed stochastic, it sees that it received a masked array, and it knows that it's got some work to do. And specifically what it does is it essentially breaks things down and says, these things are unobserved stochastics, they're variables essentially in my model, and these things don't change. And so it runs things, it essentially sets up two separate objects under the hood here. So the only change I have to make is to go into PyMC and create the masked values and pass those masked values to the Poisson instead of the original data. So that's the only change you have to make. And it will impute those two missing values. This is what I was talking about, using a function to encapsulate my model. So here I define my model here, and then I return the locals at the end, and it's just going to return the dictionary of all the variables in that namespace. And so now I can run this missing data model. And now, note if I tried to plot, I need to do this. If I tried to plot the data, or an observed variable in a regular PyMC model, it would have nothing. It doesn't have a trace, right? Because the variables don't change. In this case, it has two traces corresponding to the two missing values, one of which was in the early part of the time series, so it's got a larger expected value. The other was in the later part, and you can see. And so there's still considerable uncertainty about what that value is. And that value, and the nice thing about it is that uncertainty, the uncertainty from the whole model is propagated into that missing value. So there's two components to that. There's the epistemic uncertainty about the true values of the parameters, but then there's also sampling uncertainty, right? Because this is a draw from a Poisson distribution, no matter what the value of the parameter is. So it includes both of those sources of uncertainty, which is nice. That's what makes it a draw from the posterior predictive distribution, not just the posterior. Posterior doesn't include sampling variability. Okay? The nice thing about PyMC 2, I haven't talked about PyMC 2 versus PyMC 3 yet. PyMC 3 I wanted to use for this, but I just didn't feel it had come far enough yet to teach to an intro class. And PyMC 2.3 is pretty rock solid now. They're pretty similar in terms of syntax, and we hope to, this time next year, be able to give a PyMC 3 tutorial. But one of the things that PyMC 3 doesn't do yet, that PyMC 2 does, is it automatically assigns a MCMC algorithm to the stochastics in your model based on their appropriateness. And so there's a little method that gets called automatically every time you specify a model that's called the competence. So every sampling algorithm has a competence method that, depending on the variable that's passed to it, it kind of says whether it's good or not at dealing with that. As an example, is if you pass data that's binary, true falses, Bernoulli draw sort of things. It doesn't make any sense to use a regular Metropolis algorithm there because it would be very inefficient, right? What's the chance of proposing exactly 0 or exactly 1 using this? Well, there is a binary Metropolis algorithm in PyMC that anytime it sees Boolean data, I'm using binary Metropolis because it only ever it only ever proposes 0s and 1s. And so it'll go through and do that for you. And in fact, you can look at any given model. There is a dictionary called Step Method Dict that tells you which which MCMC algorithms have been chosen. And we can see that for late mean and early mean, it's Metropolis. Might have picked Slicer. Some of you might see Slicer in yours. It's the slice sampler. And the switch point is discrete Metropolis. So it's not quite the same as binary Metropolis, but similarly, it's only going to pick discrete values. It's not going to propose 3.2 for something that can't take floating point numbers. And so you can, if you want to override PyMC's automatic choices, you can use the method called use step method. So I explicitly want to use the slice sampler for the late mean. And that's fine, and it'll do that. And you do that before you sample. After you declare your model, but before you sample. I didn't talk about slice sampling, it's just no time. But it's just another method that's pretty prevalent. Bugs uses it a lot. And I've just added it recently to PyMC 2, so I think I was a little ambitious with it. Any questions about that piece? Kind of the internals? Quick tour of the internals? What's going on? Yeah.
So I've been playing with the sample size and just adding another order of magnitude on samples and and every one that I've looked at still looks, I would call it significant.
It's not going to reduce it. It's not going to reduce it. But if your effective sample size is, so in other words, if you're highly autocorrelated, the effect of taking more samples on your Monte Carlo error is not going to be as high. So you need more samples to get the influence of the same influence as independent samples. Right? So the stochastic, the kind of strong law of large numbers dictates that if n goes to infinity, things are going to approach the true value, the true posterior, the true integral. Well, how close to infinity you have to get is larger if things are highly autocorrelated.
But there's not a direct connection between the amount of autocorrelation in the trace and the quality of the inference.
Quality in the sense of it'll take longer to get rid of the Monte Carlo error. So you're going to, if you go back up here and look at my summary thingy, not to get technical, summary thingy. Where is it? Oh, here, I'll just call it. So if I go M, early mean, summary, I get this MC error here. You want that to be, orders of magnitude smaller than that. Okay, it's 2 orders of magnitude smaller. I'm happy. But sometimes it takes longer for that to go drop. Right. And that's what will be affected by autocorrelation. We're not worried. So, some people freak out when, so you can thin things. Thinning will help, right? If you see, so this here, if I thin this by a factor of 40, golden. I've gotten rid of the autocorrelation. But I've just thrown away every, 39 of every 40. Why not just take more samples? You do this, you need them anyway. So whether you thin for n or take n times 40 iterations, it doesn't matter really. You can get the same number of samples. That's all. Some people, like Charles Geyer said, just never thin. Don't worry about thinning. Some people are militantly against it, and some people like it. It's just whatever you pick your poison. Sample more or thin. Okay. Yeah. Based on the stochastic nodes that you pass it, it'll dig in there and it'll say, what kind of data type is this, and is it positive all the time? You know, it looks at various things.
But in this case,
That's because I changed. So I released 2.3.3, and I gave slice sampler I made it really, you know, I was aggressive with it, and I probably should have just left. When you see 2.3.4, it'll have Metropolis being back in the driver's seat. It's no big deal most of the time, but I think Metropolis is a better general choice. So. We don't have time to go into it in too much depth, but what essentially happens with the slice sample, if this is our posterior distribution, it takes two slices. So it starts at, you know, wherever your current theta is, theta naught. It takes a slice in this direction. And so it defines basically this piece here. And then it takes a slice, takes a random number in that interval and finds a slice here, and then draws uniformly under that slice. And so it'll pick a value here. So my next value is going to be that. And it'll do that again. It'll do this, and then it'll randomly pick a slice here, and then it'll draw another value. So it doesn't require accepting, rejecting. What it does under the hood is it grows and shrinks this slice so that it contains most of the support of the distribution. It doesn't want it to be too long. It doesn't want it to be too short. That's all. And it can work better in some instances. It becomes an art after a while. It's like I've just cured problems by switching from Metropolis to slice and back and the other way around. All right. 1 hour. We have 1 hour left. All right. So just a little bit more in depth about PyMC and how you build models in practice here. I've talked about stochastic and deterministic objects. There's also a third one called a potential. This is what's known as a factor potential, and you don't see it in a lot of models because it doesn't really represent a node in the graph. What a factor potential is an arbitrary log probability term. And they're actually super useful because you can use them to constrain your model in some way. So you can say that a variable has to be, you know, greater than 1, or greater than 1, or it has to be, or the different, if you had two switch points, you could say this switch point has to be lower than the other switch point. They can't cross over at any point, those sorts of things. There's nothing wrong with doing that. You're just adding a log probability term to your model. But I just want to go through each of the classes and how you use them. So stochastics have two important attributes. The value, which changes if it's not observed, doesn't change if it's observed, and a log probability. And every time the posterior of the model gets calculated, that log probability is evaluated. It does nice things like it caches them for you. It only reevaluates when it needs to, that is when its parents change. So if the children of a particular node has changed, it doesn't affect the log probability of that node, and so it doesn't get reevaluated. So it's pretty efficient about not recalculating the whole model at every iteration. There are three ways of creating a stochastic variable. One is the so-called automatic, and the automatic requires PyMC having a stochastic node that represents a particular distribution. And so we've seen these already, right? So discrete uniform builds the stochastic, adds the discrete uniform log probability underneath, and does all of that for you. And so this is the best way to do it if they're there. Same thing, exponential, what have you. The other way, and so the nice thing is that when PyMC doesn't do what you need it to, you can totally make one up on your own. And so the other way is to use the decorator. So we saw the deterministic decorator. Well, there's also a stochastic decorator. And a stochastic can be used to wrap arbitrary stochastic nodes. All that's got to happen, it's got to have two things. It's a regular Python function, except it has to have a value argument, which gets turned into an attribute, and it's got to return the log probability of something. Okay? It's up to you. You can screw it up all on your own after that. But as long as it's got those two things, PyMC will work with it. So this is an example. This is a switch point discrete, it's not even discrete. This is a uniform log likelihood, a log probability. So it takes values between 1851 and 1962. If the values are outside of that, it returns a negative infinity. Otherwise, it returns the uniform log likelihood. Only difference here is that it's not enforcing any discreteness. Okay? And all I did was wrap that in stochastic. So if you have your own crazy log probability, you can, as long as you can write it in the form of a function, you can include it in PyMC. Let's see. The other way is what we would call the direct instantiation. That is, you actually call stochastic, capital S stochastic, on your own, and you pass it everything it needs as arguments. So here's a log probability. Here's a random number generator. If you call random on this node, add the doc string, parents, whether you want to trace or not, d-type, random number seed, everything. I've never, ever done this. But you can. Data stochastics, similarly, as I said before, the automatic is the same. All you do is you add that observed equals true flag, and you're done. The decorator is just observed rather than stochastic. You can, this is more of an anachronistic way of doing things, but you can go stochastic. Nothing wrong with doing that if you want to, but it's easier just to do that. Okay, and so this is the Poisson log probability. And so I call, this is, if I, for some reason, wanted to use SciPy's probability mass function, maybe if it was faster or something, I might use it. And so all it does is returns the log PMF of the value, and the only difference is that value will never, ever change because I've fixed it. Okay? Deterministic, I already showed you. So deterministics, notice, don't have a value, and they don't have a, they have a value, they don't have a log probability associated with them, right? They do have parents and children, and they don't have any methods. So similar thing. There are some automatic deterministics that some people don't know a lot about, actually. There's a linear combination for doing linear combinations of things automatically. One of the best ones I use the most is lambda. So if you've got a really concise function that can be written as a lambda statement, you can specify it as a lambda object. A thing called a completed Dirichlet, which, if you know what a Dirichlet distribution is, this just completes the probability simplex, so it adds to 1. So it can be used as the prior, so it can be used as the probabilities for multinomials and things. There's a logit, so if you're using the logit function for like a logistic regression model, and so on. You can, so generally if I have a deterministic node, I either have to write this rate thing here or use a lambda. For some of the basic arithmetic functions, you can actually create two stochastics or two deterministics, whichever, and just add them. So here I've created a multivariate normal and another multivariate normal, and I added them together, and what I get down here is this PyMC object deterministic, and its name is x add y. So they're kind of hard to access later on. So if you want to give it a name, I would do this. I would go sum xy equals lambda sum xy. Okay, I would do that, except I messed it up. Oh, there's no equals there. Oh, and I didn't import it. Okay. And now it's an object with a name. So it's really all you give it is gives you a name to refer to it by. Okay. Already seen the decorator version of the deterministics, and direct is the same thing. So I can call deterministic the deterministic object instantiator itself. One really nice thing that Pymc has is a notion of a container. And a container is just a data structure that encapsulates several stochastic or deterministics in one object, essentially. And where this is really useful is, for example, in something like a time series or serially dependent variables. So here's an example here. Let's say we have x naught that is normally distributed with a mean 0, but then the subsequent x's, their means are the x from the previous in the previous element in the array. So I've got a whole series of serially dependent stochastic variables. And so what I'd have to do is manually go in and, there's like 100 of them, I'd have to have 100, normal x naught, and then normal x1 depending on x naught, and so on, and draw that big ugly DAG. What I can do in Pymc is actually build a little loop like this, and all I have to do is have some sort of container for them. So in this case, I chose a NumPy array. I could have made a list as well, and then iterate and essentially populate that array. When I pass that to Pymc, it actually digs in to those data structures and discovers Pymc objects in it. And one of the nice things about it is that they will be jointly updated. They will be block updated. So one iteration of the Metropolis will involve updating that entire vector of parameters at the same time. You can do it even more succinctly in a list comprehension. That's what I do most of the time. And I just give them unique names that way. Here's that potential, factor potential I was talking about. So, you often want to constrain your model. So, there's some sort of indicator function where, where you've got, this is exactly the situation I was describing, where let's say, we knew that the rate in the second, period of the disasters model has to be smaller than the early rate. So we can constrain it that way if we want to. It's kind of cheating because it means we looked at the data, right? Or unless, it could be something we knew ahead of time, but you can do that with a factor potential. And this is how we do it here. We use a potential decorator. There are no automatic ones. And the thing about the potential is it has no value because it's not a node in the graph. All it does is return log probabilities that get factored in. And so you can see here that, if this condition is not true, it returns negative infinity, which will completely blow up. There's no way of accepting a negative infinity here, right? Similarly, a direct one, okay? Exercise. That bioassay model, can we do that in Pymc? This should be easy. Um, 4:15. So bathroom break if you need it, but maybe just think about it for a second and write a few things down. Maybe I'll do it as well. It'll probably take you, longer than a couple of minutes, but just using Pymc objects now instead of rolling your own. We'll fit it later. We're just specifying it here.